With Maxwell's correction to Ampere's law, we have now seen Maxwell's equations in their final, form. And we've throughout the course we've been kind of going through iterations of Maxwell's equations. So I want to take this video just to summarize, those equations because they're so important to physics and they're so important to electrical engineering. In the top table are his equations in their most general form, and you could see these in a few different versions or a few different iterations. But for example, you can introduce an epsilon zero into D and make this an E because you know that the electric flux density is the permittivity times the electric field, right? And so you can go back and forth between D and E by introducing epsilon zero into these equations. And similarly, you can go back and forth between B and H by introducing mu zero into these equations. However, these you might argue are the most kind of beautiful, the most beautiful form of these equations because they don't have epsilon zero or mu zero in them at all. So in this first column is the point form or the differential form, and the second column is the integral form, and then we've given these the names, right? And these four equations, they contain the entire theory of electromagnetics in just those four things. And so for something to qualify as an electromagnetic wave, it must satisfy all four of those equations. So you might ask, well, what types of things satisfy all four of those equations? And the things that satisfy them, it turns out, are light, microwaves, gamma rays, X-rays, infrared, ultraviolet, radio waves. The integral form, as we've said before, describes physical situations like the flux of a magnetic field through a surface is equal to zero, while the point form is usually more useful in making calculations. The names we've been over, right? Gauss's law, then Gauss's law for magnetic fields. Monopoles do not exist. Here's Faraday's law. A change in magnetic field creates an electric field. Here's Ampere's law. With Maxwell's correction, a change in electric field, derivative of D with respect to T, creates a magnetic field. And then, as we started the course, we've said this a few times now, if nothing changes, then the derivatives in these equations are zero, and then we have what's down here in this table, and these are the electrostatic equations. So the electric quantities D and E, you'll see then are completely independent of the magnetic quantities B and H. So therefore, as we've been saying, in the static case, we can separate the two phenomena into electrostatics and magnetostatics, and that's what we've done in the first half or so of the course. But the remainder of the course is regarding changing electric and magnetic fields, which we call dynamics, EM dynamics. And in this case, the top table only applies, and we cannot separate the E from the M. We cannot separate electric fields from magnetic fields. Now, in the next video, we're going to consider special types of changing electromagnetic fields called time harmonic fields. So let us take a look at those. Thank you.